Okay, is the screen visible to you? Sequential statements part 2.
Yes, sir.
Okay. So we'll start with that. So another statement that we come across as far as sequential statements are concerned is the wait statement. Now the operation of wait is sometimes similar to that of if. See, that process is another sequential construct. In fact, process itself is a concurrent construct, but whatever is there inside the process are all the sequential statements. And we said that process cannot have a sensitivity list when we are using wait statement somewhere inside the process. So please make sure that whenever you use wait statement, the process in which it is encapsulated does not have a sensitivity list. There are three different flavors of wait statements. One is wait until, wait on, and wait for. Let us see each one of them one by one. So syntax for wait until, it is simply wait until some condition is met with, whatever is the signal condition. The wait until statements will accept only one signal. So you can say that it is more appropriate for what is called as a synchronous code rather than asynchronous code. These are small tips which are very, very essential when you start writing a bigger design. Since the process has got no sensitivity list in this case, wait until must be the first statement. Again, very, very important here that wait until must be the very first statement in the process. This process will be executed every time the condition is met with. Let us see the example, a simple example of 8-bit register. So process, as you can see, there is no sensitivity list there. Begin, wait until. So this is the very first statement, as you can see, as we have already seen, the requirement for wait using wait until. So it is a clock tick event and clock equal to 1. Whenever you see such clock tick event and clock equal to 1, it means that it is the yes. What? What does it signify? Guys? Guys, answer the question, please. Hello?
Yes, sir.
What does the statement imply? Clock tick event and clock equal to 1. What do you mean by that? I mean, what sort of hardware can you visualize? Come on, tell me. Come on, please. No answer? No answer?
FF, a DFF.
No. What you are trying to do here is you are trying to trap the positive edge of the clock. This statement always means it's the positive edge of the clock. Understood? So clock is a signal somewhere which we will be defining, which is actually going to change. It's a clock, remember. And whenever there is a change in the clock, and then we are seeing the direction also, that when clock is equal to 1. So the moment the clock signal asserts or becomes equal to 1, that is the positive edge. Only clock tick event will mean that it is simply trying to trap the change in the clock. Whereas clock tick event and clock equal to 1 means it is a positive edge that you are trying to trap. How should I change it to negative edge? Very simple. How do I change it to negative edge? Come on.
Involve or clock equal to 0.
Correct. Clock tick event and clock equal to 0. All right. So that is the very first statement. So this process will execute whenever there is a rising edge of the clock. Very first thing. And then you are checking something like if with RST, most of the times RST is nothing but the reset. That is the reason why it will be called as RST. So RST equal to 1. If reset is asserted, then output simply is all zeros. Obviously, the register output of the 8-bit register should be equal to 0 once it is reset. Else if clock tick event and clock equal to 1, So when we are checking whether it is a positive edge of the clock, and then output is assigned whatever is the input. All right. So this is basically how you will use the wait until statement. Okay. Is it okay?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
This is what it infers. Okay. So you can see it is an 8-bit register. In fact, register means nothing but a collection of flip-flops. So all these are all 8 flip-flops. Okay. And we are having one clock signal, reset signal, input, which is 8-bit, output, which is also 8-bit, obviously. Okay. So as you can see from here, the simulation output, that the output changes only with the clock. So look at the clock signal carefully. All right. So here you'll see that this part, that now my output is asserted, is whatever the input C8, for example, will be transferred over here at the output, at the rising edge of the clock. And as soon as there is a reset, what is going to happen? The output should be equal to 0. But why it is not going 0 immediately? You see here?
D flip flop.
No, because we are looking at a synchronous reset. So this is called as the synchronous reset. I think I have already discussed this when we discussed the D flip-flop and the if statement. All right. So there is a difference between synchronous and asynchronous. Synchronous would mean only when the output will change, output even reset also will happen. The output will be reset only when rising edge of the clock occurs. Okay. Whereas if it would have been asynchronous, then immediately as soon as the reset signal was asserted, immediately the output should have gone 0. That would mean it will not wait for the rising edge of the clock. Okay, so that is the basic difference between the synchronous events and the asynchronous events. Then the next is wait on signal. Wait on. Okay, the wait on accepts multiple signals. This is interesting. Okay, earlier wait until was having only one condition or one signal condition. Now here you can have multiple signals. The process will be put on hold until any of the signal listed changes. Okay, so again, a similar kind of thing. In fact, the same thing, but with different syntax for wait. So process, again, observe that there is no sensitivity list. Begin. Wait on. Now here you are having multiple signals. Wait on clock reset. Okay, so any one of these signal changes, you are going to get, you're going to execute the process. So if reset is equal to 1, then output is 0. Otherwise, if clock tick event and clock equal to 1, then output is assigned input. Okay. So now if you see, what is the difference? Can you tell me what is the difference that you see?
As soon as the
As soon as the reset is asserted, the output
output
is 0.
goes down to 0. Yeah.
So can we say that this is asynchronous reset? Yes or no?
Yes, sir.
Definitely. This is an asynchronous reset. Okay. So you have different ways and means. So different statements can be used to implement different, let us say, types. For example, synchronous and asynchronous. So this is basically what the wait on statement does. Now we are going to revisit the D flip-flop with wait. Earlier we had done this with other sequential statement, but now we are going to use wait. Complete code is there in front of you. So library IEEE, use IEEE, that usual thing, entity declaration along with the ports, architecture, and then we have the process. Inside the process, we have wait on RST and clock, exactly the same code that we had for the 8-bit register just previously seen. Q is reset, that is 0 when RST is equal to 1, else the rising edge of the clock, that is a positive edge of the clock, you have D assigned to Q assigned to D, or the other way around, D assigned to Q. So that is how you will be writing the design for a D flip-flop using wait on. Okay, this is what it does, and you'll see that it is nothing but the same thing. Okay, all right. So the another syntax is wait for. Okay, so three types of wait: wait until, wait on, and wait for. Now wait for is time. The argument that it takes is time. Okay, so wait for is intended for simulation only. Okay, specifically this is used in the test benches, so where you will be requiring automated signals at predetermined times, then only you'll be using this wait statement. Remember, this is not for synthesis. Okay, the next type of sequential statement is the case statement. So case statement is another statement which is, as I said, a sequential statement to be used in sequential part of the code. Obviously, it means that it has to be used inside the process. It is very similar to the when statement, but remember that when was a concurrent. When was a concurrent kind of statement. Okay. Now here in this case, all permutations must be tested. So the keyword others is always will be helpful. We have seen some similar kind of thing earlier. Another important keyword is null, the counterpart of unaffected. In case of when, we were saying that, okay, if we don't want anything to happen for that condition, you would write unaffected. Here it would be null. So that is used when no action is to be taken place, to take place. Case allows multiple assignments for each test condition, while when allows only one. This is one very important difference. This is the syntax. Case expression is when choice is something, or when choice is something, and end case ultimately. Okay, so where you can use it, as you can see, inside the process, inside a function, inside a procedure, inside if construct also, and inside loop construct also. What are the rules? The expression must not be enclosed in parentheses. Okay, type of expression must be enumeration, integer, physical, or a one-dimensional array. Every case of expression must be covered once and only once by the choices. Okay, what does it synthesize to? Assignment will generally synthesize to multiplexers. Okay, incomplete assignments in clock process will lead to a flip-flop. In unclocked, it will lead to transparent latches. This is a very dangerous thing. As I said, unintended, let us say, inference after synthesis will consume your resources if it is not intended that you have a latched output, or maybe even a latched, even a flip-flop registered output, as it is called as. In that case, uh, incomplete statements will give you this kind of problem. This we have faced already when we were talking about if also. All right. As I said, incomplete statements in clock process will synthesize to registers. Registers means flip-flops, collection of flip-flops to be more precise. Example, case address is. So address is the uh, deciding, let us say, uh, mm, condition. So when address that is 0, say you execute some statements like a is assigned 1. When 1, a is assigned 1. Okay, it doesn't matter. B is also assigned 1 here. When 2 to 15. So we have a range of address values. Okay, C is assigned 1. When pick out several different addresses, that also is possible, 16, 20, 24, whatever, then this condition. And when others, you see it is null. So I don't want anything to happen apart from these conditions. That is called as a mopping up. Okay, so that will lead to such a kind of thing. Have you understood the use of case? It is very similar to switch statement in C. If you have done C language, you'll really understand this. Okay? Is this fine?
Yes, sir. Yes, sir.
Okay. So we are going to construct a 2-digit counter with a 7-segment display, and supposed to be a progressive 2-digit decimal counter. That is, it goes from 0 to 99 back to 0 with external asynchronous reset plus BCD for the 7-segment conversion. Okay, BCD to 7-segment conversion. So this counter, we are going to design a counter. Okay, this counter can be reset asynchronously, and of course the clock will generate the advancement in the count. So this is the complete code. Go through it very carefully. The usual library IEEE declaration entity. Now the counter entity is having the ports clock reset digit 1, digit 2. I need not tell you what other things are. Output, of course, for digit 1 and digit 2 are how many? Digit 1, how many bit counter? How many bit output? Logic vector, STD logic vector. What is the size? 6 down to 0 means what? How many?
7.
7. Because we are supposed to interface it with a 7-segment display.
Segmental LED.
Correct. So architecture, counter of counter. I've written the same name for the architecture also because it is only a single architecture here. Begin, process, clock and reset. What does this first statement mean? Process in brackets, clock and reset. What do you mean by this? Clock and reset are a part of what? The sensitivity list. All right. So this process will be executed only either when clock changes or the reset pin changes, signal changes. Okay. I'm declaring variable. Now please remember this variable is a type, again, as we have already seen, signals and variables. So this will exist. This is something like a local variable. So this will exist only inside the process. Remember this. So temp1, I'm declaring it as a range integer of type integer, range 0 to 10, temp2 integer, range 0 to 10. Okay. So there are 2 digits. Okay, temp1 and temp2. So if reset is equal to 1, then both these will be equal to 0. Else if whenever there is a clock tick event, of course a positive edge of the clock, then temp will be incremented by 1. If that overflows, that is if temp1 is equal to 10, in that case make temp1 0 and increment temp2. Okay, so after 10 clock cycles, what will happen? The temp1 will be equal to 0 and temp2 will be asserted. I mean, it will be incremented to 1. So it will be after 10, it will be 11. Okay. Okay. So if that again overflows equal to 10, in that case, temp2 is again made equal to 0. As we have said that this counter runs from 0 to 99 back to 0. Okay. So the overflow of the counter is not there. What we are doing is we are asserting, we are resetting it back to 0, starting the count from 0 again. Okay. End if. Now this is the use of the case. Now when case, the temp1 is 0. So this is temp1 is a digit, the value basically of the integer. Okay, when 0, then digit 1. What was digit 1, by the way? It was the output which was driving the 7-segment display. Okay, that will be of this combination. Okay, this actually gives you 0. The 7-segment gives you 0 output. So when 1, this is 1, 2, it will be giving you 2, and so on and so forth. Similarly for temp2 also I'm having such a kind of, so this is BCD to 7-segment conversion. This particular case statement does what? This construct does BCD to 7-segment conversion. Similarly, this is for temp1. For temp2, that is the second digit, this is the BCD to 7-segment conversion. So this is what we get at the output. So as you can see, it is all in hex. So it is not possible for us to immediately see in binary, but then you'll see that whatever is intended is got over here. All right. For example, 7e. So this is 7e means 0. Okay. Whereas 30 means equal to 1. So this particular combination gives rise to 1 display on the 7 segment. Okay. So the sequence would be the 0, 7e, 30, 6d. So you can see here 30. This should be 6d. Because of the space limitations, the simulator was not able to display it. But then the next one, 7, 9, then 3, 3, and so on and so forth. Okay. And then after it counts to maximum 9, that is when the integer value is 10, then it will reset. It will change it back to 7e, which is 0, and then here it will make increment in the digit 2. All right. Is this fine?
Yes, sir.
Yes.
Okay. Now, whenever I show you such a kind of code, it is expected that you write your own code and verify yourself. All right. This is will be one of your assignments to write a 2-digit counter. This is how it synthesizes. Now, don't try to work out how this circuit works, because synthesis output can be very, very complex for us to understand. Okay. So, okay. So with that, the part 2 of statement sequential statement is done. Any doubts, any questions, please raise them. We'll start with the other statements, of course, still continuing with the sequential ones. Okay. Now the reason why I have not combined the slides into small the entire complete bunch of slides is that the simple reason is that I would like to keep the parts a little bit separate. Okay, so that you will not get confused. If I bombard you with all sequential statements in a single presentation, it becomes a little bit difficult. So many different types are there. So anyways, so this is sequential statements 3. So the loop statement. So we are going to see the loop statement here. Whenever we have the loop statement, is useful when a piece of code must be instantiated several times. So this is a repetitive kind of thing. So if you want to do this kind of repetitive implementation, like if I want to replicate the same code, the same design, the same hardware, I can use the loop statement. Like if wait and case loop is intended exclusively for sequential code. Again, that is the reason why we're calling it as one of the sequential types. So it can only be used inside a process, function, or a procedure. We are going to see functions and procedures in details. Okay. There are several ways of using loop. Loop is an infinite loop and thus an error unless it contains an exit or wait statement. So loop should never be infinite. Infinite loop means what? From hardware point of view, software, that's fine. It will keep on doing that looping for infinity, let us say, up to infinity, unless and until you break it. But in case of hardware, this is going to be a disaster. Why? Can you tell me what is the reason, guys?
Hardware would be overworked, heating.
Well, not really. See, you have still not come to the
Waste of a spike.
you still not come to the idea that what we are doing here is we are generating or synthesizing hardware. You cannot have infinite hardware, can you? Your resources are limited. You cannot have, if I make a loop and if I put implementation of a flip flop, for example, so you cannot have infinite flip flops. Simple as that. Because the resources on your target device are limited. So there should never be this kind of infinite loop inside in any VHDL design. This is the syntax. Loop label is again optional. You can have a couple of sequential statements and loop. Then there are little variations in the loop as well. For loop, this loop is repeated a fixed number of times. So the syntax goes like this: for some identifier in range loop, end loop. Okay. And there is something called as while loop. The loop is repeated until a condition no longer holds. So you can write while this condition is true, loop, and you can have so many different iterations to that loop. We'll see an example. Wait will continue looping until exit used for ending the loop. Okay. So this is a very important thing. Next is used for skipping the loop steps. Okay. So what are the various important things associated with the loop? Wait, exit, and next. Okay. For example, this loop will be repeated unconditionally till I reaches a count of 5. That is, it will go 6 times. It will be iterated 6 times. So for I in 0 to 5, remember this carefully. For I in 0 to 5, I'm specifying a range 0 to 5, whatever. Try to understand what this is. There is some statement over here, and this will continue looping on. Okay. So for I in 0 to 5, do this repetitively. All right. One important remark for loop is that both limits of the range must be static. So this 0 and 5, these should not be dynamic. They should not be rather changeable. Okay. Immutable, as it is called. Okay. So these are immutable. So thus a declaration of the type for in 0 to choice loop, where choice is an input non-static parameter, is generally not synthesizable. So when your choice is an input which is non-static, that which is changes, if this is changing, then in that case it will not be synthesizable. Because if you are implementing, again, a very logical thing, that sometimes I want 10 flip-flops, sometimes I want 50 flip-flops, that will not be there, no? So it cannot be synthesized. All right. So this 0 and 5 both have to be static. I mean 0 to whatever choice. This is the example of while loop. So while I less than 10 loop, wait until clock tick event and clock equal to 1. That is the positive edge of the clock. Do your job. Okay. The loop in this example will keep repeating while I is less than 10. Okay. We have the specific condition over there. Okay. All right. This is the example for exit for I in data tick range. Okay. This is again an attribute of the data. We'll see that attribute again, revisit it again. So data tick range means what? The range of the data. Loop, do whatever you want. But when another condition is met with, for example, other than this, in that case, you have to exit the loop. Exit implies not an escape from the current iteration of the loop, but rather a definite exit. That is, it is going to terminate the loop. That is, even if I is still within the data range, the loop statement will be considered as concluded. So this is a direct exit. Okay. So in this case, the loop will end as soon as value different from 0 is found on the data vector. That is what you have to see here. This is for skipping. For I in 0 to 15 loop, next when I is equal to skip, okay, jumps to the next iteration. So this next causes loop to skip one iteration when I is equal to skip is some value. Okay, skip is some value. Skip is not a keyword, please remember that. So this is some value. So at a particular value, I want it to skip to the next loop, next iteration. So next causes loop to skip one iteration when the value of I is equal to skip. Synthesis. It is generally not synthesizable. Some tools do allow loops containing wait statements to describe implicit finite state machines, but this is not a recommended practice. So in your table, you have to again make sure you make the correct entry of loops as generally not synthesizable. Okay. This is an example for 8-bit unsigned carry ripple adder. We already have the equations for that. Sj, that is the sum, and this is the carry. So Aj XOR Bj XOR Cj, that is the sum, and this for the carry. Okay, so we want to implement this using VHDL. How to do that? So A is your input, B is your input, C in is input carry, C out is output carry, and S is the sum. So as I said, you'll have all the full adders. It's a let us say an array of full adders. Okay, and it will be connected like this. So carry of first full adder goes as input, carry in of the for the second one, and so on and so forth. Okay, and then finally you'll see the sum over here. So this is how the code will look like. Again, the library declaration entity adder is generic. Now again, I'm using a generic here, okay, of the name as length, which is of integer type, and the value is 8. Okay. Again, declaration of the ports, C in, C out, A, B, everything like that. Okay. See here, since it is generic, I can write here as length minus 1 down to 0. So if 8, the length is 8, then this will be 7 down to 0. Okay. Not necessary to use generic, but it is a good practice. Because if I want to implement a 16-bit kind of output, in that case, I can simply replace this 8 with 16, and that's the end of it. Okay. Architecture, begin. So my process sensitivity list is A, B, and C in. Variables are carry only in this case, std logic vector length down to 0. So this is a 9-bit. Okay. We require this to be 9-bit because as you can see here, this will have additional input from input side, additional bit from input side. So that is the reason why we write is length down down to 0, that is 9-bit. Okay. So begin carry 0, that is index 0 is the first, that is the LSB. LSB of that carry vector, carry std logic vector variable will be assigned C in. So this is C in, which is assigned to that. So you can see here C0, C1, C2, C7, up whatever C8. So this is the 9-bit, 1, 2, up to C8, that is 9. All right. So I'm getting external input being assigned to the LSB of that vector. In fact, we are using it as just as a vector. It's not a bus per se. Please remember that. Okay. For I in 0 to length minus 1 loop. So length minus 1 is what? 7. So this will loop for that many times. Sum is as per our equations. Carry again as per our equations. End loop. So this actually simplifies the job. Okay. C out. What is C out? C out is a signal. And remember that before getting out of the process, you have to assign the variable to the signal. Otherwise, after doing that, if you try to write after end process, if you try to do this, it is going to create an error. Error in the sense, this carry will not exist outside the process. Simple as that. So before exiting the process, you have to assign it to the signal. As I said, carry here in this case is a local variable. Signal roughly is a global variable. This is the output that we get. Okay. You can just verify this code also. All right. Now, before we go further, one more example of the circuit should count the number of leading zeros in a binary vector starting from the left end. So it should count the number of leading zeros. Okay. So try to figure out what you will have as your hardware. Try to figure that out. Meanwhile, let us see how to go about it. So I will start from the left side. So this is the leading zeros, the very first zero. So my counter goes up, 2, 3, that's it. Okay. So this 3 leading zeros is what we are supposed to count in this case. So this is the code for that. Library IEEE, again the same thing, port declarations. Now my output is zeros because I want to count the number of zeros. So it is out integer range 0 to 8. Maximum there will be, let us say 1, 2, 3, 4, 5, 6, 7, 8, obviously zeros. Okay. So this is the architecture for that. Now, whenever there is a change in the data, this process will be executed. Variable, I've declared a variable called as count, again range 0 to 8. Begin, assign that count as 0. So whenever there is a new data available, this process will be executed for I in data tick range. Okay, loop. So range, we already know what is the range for the data. Okay, fine. So case data I. Data I means what? When I is 0, that is the very first iteration through the loop. That is, I'm going to see the very first this thing over there, bit over there. When if it is 0, add the count, otherwise exit it. Okay. So this is what will happen. As soon as it encounters anything other than 0, it will exit the loop. Okay. Then I assign this count to zeros. Remember that zeros is again a signal. So I have to assign count to zeros before I exit the process. So this is what we get. So 3 zeros, you can see here that it is working as per our expectations. Now as a kind of assignment, you can modify this to trailing zeros. Instead of leading zeros, write a code to test the trailing zeros. Okay, it's a little bit challenging. All right, so that was the third part. Any doubts, any questions till this point?
No, sir.
Okay, right. So I will again switch back to the time has come for us to compare between concurrent and the sequential constructs. Okay, so that mops up, sums up, concludes whatever statements we have seen. Okay, for example, case versus if. In principle, the presence of else in if-else statement might infer the implementation of a priority decoder, which would never occur with case. Okay, this will generally not happen. When if, that is a sequential statement, is used to implement a fully combinational circuit, a multiplexer might be inferred instead. So please, you have to be careful about this. All right. Therefore, after optimization, the general tendency is for a circuit synthesized from VHDL code based on if, not to differ from that based on the case. So generally, the synthesizer will keep the two things, the inference of the two things in a similar manner. Same inference as we can see with if as well as with case. So if cell is equal to 0, then X is assigned A, else if cell 0, 1. So this is a multiplexer, as you can see. With case also, a similar kind of construct will be inferred. All right, exactly the same inference will be there. Now case versus when. Case and when are very similar. However, while one is construct, that is when is construct, and case is sequential. So just this table tells us a lot. When is concurrent, whereas case is sequential. Usage only outside process, functions or procedures. This is only inside process, functions and procedures. All permutations must be tested. Yes, both the cases require all the permutations to be tested. Maximum number of assignments per test is 1, whereas this is one of the biggest difference. No action keyword is unaffected here and null here. Okay, so many times comparing sequential and concurrent constructs will give us a proper insight as to when to use a particular construct. But again, you can have the same functionality. So as I said, you can do the job in different number of ways. So here in this case, with cell select, X is assigned A when the cell is all zeros, B when equal to 0, 0, 1, C when 0, 1, 0, unaffected when others. So this is what is required. The same thing you can implement with a case statement. Okay, so you can just see over here. One major difference. What is a major difference over here is that here you have to use unaffected. Here you have to use null. Now using sequential code to design combination circuits. Again, there is a misconception always in case of beginners that sequential code is used for only sequential type of circuits like FSM. No, sequential code can also be used for designing combinational circuits. Okay, so in fact, it will be used for either sequential or combinational both. Resistors are for sequential circuits necessary, so will be inferred by the compiler. Now this should not actually happen for combination circuit. So even if you use a sequential code, it should not somehow infer what is called as the resistors or the flip-flops. As we have already seen that unintended flip-flops or or latches, transparent latches will be created, which may not be really intended. In fact, it is wastage of resource also. Also for combination circuit, complete truth table should be specified. Incomplete truth table will lead to problems. Rules to be followed while using sequential code for designing combination circuit. This is very, very important. Rule number 1, make sure that all input signals used in the process appear in its sensitivity list. Very important. Okay. Rule number 2, make sure that all combinations of the signals input output are included in the code. Make sure that by looking at the code, the circuit's complete truth table is shown, is covered. Okay. Failing to comply with rule 1 will generally cause the compiler to simply issue a warning saying that a given input signal was not included in the list and then proceed as if the signal were included. Even though there is no damage caused to the design, it is a good design practice to take rule number 1 in consideration, because this gives you a concise picture later on what sort of process statement you are using. What are the important things that are changing? That is the sensitivity list. With respect to rule 2, the consequences can be more serious because incomplete specifications, that incomplete statements, may cause the synthesizer to infer latches in order to hold their previous value. So this is rule number 2 is especially more important. We'll see a bad combinational design. Okay. So what we intend to do is have a multiplexer. Okay, something like this. So select is 2-bit. As you can see here, X and Y are the outputs. A, B, C, D are the inputs. Now X should behave as a multiplexer, that is, should be equal to the input selected by the cell. Okay, this vector. Y on the other hand should be equal to 0 when a particular combination of cell appears. Okay, that is 0, 0 and 1 if in case of 0, 1. So it superficially it looks very simple. Okay, so if I write it like this, again, library declaration, entity declaration, and architecture. So in architecture, if I write A, B, C, D, and cell, obviously all of them have to be included in the sensitivity list. Begin if cell is equal to 0, then X is A. All these things will be as per our expectations. So you see that, okay, what is the problem? Okay. So functionally it looks okay, but this is what happens. Value of Y remains 1. Here in a particular combination, see that? Because combination, the last combination, you see here, it was not included in the last combination. Y was not included. What is the value of Y? It is not defined here, so it is incomplete. And if it is incomplete, the last value of Y will be retained, which is actually a latch. So the simple cure for this will be mention Y here also and here also, but make them unaffected. Okay, or don't care. All right, so this is one basic, very important thing that you should remember. Okay, these are some templates. I want all of you to write down these templates, because the templates, using these templates, you can construct your own design for process which gives a purely combinational design, for a process which gives transparent latches plus logic. So write this down. Of course, I'm going to give you the PDFs, but you have to, at one point, you have to use pen and paper to write this down. Otherwise, you'll never understand. Only reading will not do. You have to write it sometimes. Guys, are you there? Yes?
Yes, sir.
Yes, sir.
Yes.
So complete this,
Yes, sir.
write it down and then tell me whether you completed. Okay, have you finished?
Yes, sir.
So using these templates, you can either have a pure combinational logic also, and if you want, you can have some transparent latches as well as logic also. This is for flip-flops and logic. So I've categorized it as something like pure combinational, then latches plus logic, flip-flops plus logic, okay? And an alternative way also for synchronous and asynchronous actions. So copy this down as well. Tell me once you are finished.
Done, sir.
Finished?
Yes, sir.
Okay. This gives again flip-flops plus logic. So there are various ways in which you can do the same thing. Finished with this?
Yes, sir.
Okay. Let us see how we can implement a random access memory. Okay. The figure will be something like this. So you have this random access memory. You have data in, data out. You have to provide the address, okay, clock, and write enable. All right. So this is what is expected. So circuit has data input bus. See, I'll tell you a simple way in which to come out with correctly interpreting the design. So, for example, if you have been given such a kind of figure, so it is better if you write it in your own words as to what you have understood from the figure first of all. Okay. So this is what it does. Circuit has data input bus data underscore in. That underscore is not visible here, but it is there. Data output bus data underscore out, and the address bus ADDR, a clock signal CLK, and write enable pin. Okay. So when enable is asserted, write enable is asserted, at the next rising edge of the clock, vector present at data in, that is here, must be stored in the position specified by the address. Okay. All this. Output D out, data out, on the other hand, must be constantly display the data selected by address. Okay. So see, there are two important things that we must understand, that while writing the data, address will be pointing to a particular section where the data in is to be stored, and at the same time data out will be displayed, or let us say it will be output at the same address, from the same address to be more precise. Okay, so this is the code. So entity RAM is I'm declaring the entity again using library IEEE standard. Generic. Now I can go on increasing so many the size of the RAM. That is the reason why I've written generic. So this piece of code will help you with writing larger memories also. Okay. Bits as integer declared at value 8. Word. So these are the words in the memory. So it is 16 by 8 kind of a RAM. 16 bits by 8 bits. Okay. Then the port declaration. Finally, the architecture. I'm declaring a vector array. Okay, which is an array of the words. Okay, okay. These are all 16-bit words. Okay, of std logic vector. Again, how many? How many such things? 8. All right. Signal as memory, which is of type vector array. So this is a user-defined type. Vector array is a user-defined type. It is an array of it's a array of these words. Okay, and I'm declaring memory as a signal of this type, vector array type. Okay, begin process clock write enable. So this process will be executed whenever clock changes or write enable changes. If write enable 1, then at the rising edge of the clock again, then memory ADDR. So this signal at that particular address location, the data whatever is there is assigned to that particular location. All right. And if so, it was if write enable was asserted. Otherwise, whatever is at the memory, whatever is at the address index of the memory, that is output over here as the data output. Simple as that. So this actually gives us the implementation of what we have seen. Carefully see this and try to understand. It's not that difficult at all. A very essential thing, because many times you will be required to infer or design memories associated with some of your circuits. So understand this carefully. If you understand this, you'll be able to write your own memories. Fine? Is this understood? Guys?
Yes, sir.
Not at all difficult to understand. All right. So this is what is synthesized. Just have a look at the output. Okay. Now by this time you must have picked up that knack of reading the timing diagrams. Okay.
Yes, sir.
All right.
Yes, sir.
So that was the comparison. Next, we will start with the package functions and procedures. Just hold on. Okay, so is it visible now? Packages, functions, and procedures. Is it visible?
Yes, sir.
Yes, sir.
Okay, okay. So fundamental units of VHDL we have already seen, which we have covered so far. That library entity architecture, this we have covered so far. All right. Now let us see what we can say about the library itself or the package. Okay. So what is a package? Frequently used pieces of VHDL code are usually written in the form of components, functions, or procedures. We already know the contents of the package. Such codes are then placed inside a package and compiled into the destination library. Packages will allow code partitioning, sharing, and reuse, of course. So that is one very important thing as far as VHDL feature is concerned, that it will allow these packages which can be reused, shared. We will have a nice code partitioning for us to understand at later point in time. Besides functions, besides components, functions, and procedures, it can also contain type and constant definition. So you can declare certain types and then compile it into a package. Package is split into declaration and a body. So just like your entity and architecture, it is split into declaration and body. Here, package declaration defines the external interface to the package. Body contains the bodies of any functions or procedures defined in that declaration of the package. So this is how you declare the package. Write the package. Basically, the package name is some declarations end package. Okay, and the body, package name, declarations end. It will be easier if you see the example. But remember this, that when a function or procedure is placed in a package, declaration and body must conform. That is, the parameters must be identical between the two. You cannot change the references. Only definition placed in the package declaration are visible outside the package. So, as I said, common or shared declarations of types, subtypes, constants are best to be put in a package. This is a simple package. Library IEEE use again the same thing. Package declaration. Now, if I want to declare my own data type, for example, state. So it is consisting of 4 such states: st1, st2, st3, and st4. Again, this is another data type. Color red, green, blue are the possible types. Something like that. Okay. So this can also be put inside a package. So this is the package as well as the package body. This is what we have seen in the previous slide. And here in package body, my package, there will be some function. So I can have some functionality here. Okay, inside that package. So this example contains, beside type and constant declaration, there is a function also. So I can declare a function in the package, and then the package body should actually describe what the function does. Okay. Now here, since it was only the declaration of type, there was no functionality there. There is no need of a package body. But here, since we are talking about a function, you need to have a package body. Any of the packages in the previous examples can be compiled, becoming then a part of our work library or any other that you want. To make use of it, we have to add that new package using the use clause like this, use work.my underscore package dot all, whatever is there inside that package. So it is like this. Library IEEE, this is the standard thing, and this is what is the additional thing that we will be doing. Use work.my package dot all, and then you start with your usual entity and architecture declarations. Functions and procedures are collectively called as subprograms. You must be aware of the functions, specifically in C language, or maybe in case of Visual Basic, those who have an exposure to Visual Basic like things. So in Visual Basic, there will be functions as well as procedures. Similar to that, in VHDL, we do have functions and procedures. So they are collectively called as subprograms. They are very similar to process, for they are the only pieces of sequential VHDL code and thus employ the same sequential statements. So all whatever sequential statements that we have seen are or can be put inside function or a procedure. However, if case and loop are allowed, wait is not allowed. Please mark this difference. Process is intended for immediate use in the main code, whereas functions and procedures are intended mainly for library allocation. So we put commonly used programs, subprograms, and then as and when required, we call them. A function or a procedure can also be installed in the main code itself. So it's not necessary to have always to have function to be declared in a package, but you can use function inside your main code itself. So first let us take a look at the function. They are used to group together executable asequential statements to define new mathematical or logical function. If I want to define a completely new function, I can group these statements together and call it as a function. This is also used to define bus resolution functions, operators, and conversion functions. When defined in a package, function body must be split into declaration and a body. We'll see with an example here. So we have the function body, function with some parameter list, which is optional. Return, this is important. Data type is. So return data type is to be specified. We can have a couple of declarations, begin, then sequential statements, and end function. So where can function be declared? It can be declared inside the package body, inside the entity, or inside the architecture or block, generate, process. It can be defined inside another function also, or maybe inside another procedure also. However, function body is not allowed inside a package. What are the rules? The function name may be an identifier or an operator. We have already seen one of the functions long back when we discussed operator overloading. Okay, so we have already seen that. Functions cannot assign signals or variables defined outside themselves, nor can they contain wait statements. This is what we have already seen. Function must execute a return statement. This is important. Otherwise, it will end up in an error. Pure functions cannot have side effects. That is, they must do nothing but return a value. All right. There can be any number of such parameters. Even 0 can also be constant or signal. Variables are not allowed. So return variables are return, whatever you return are constants or signals, but not variables. The types can be any of the synthesizable data types, Boolean, STD logic, integer, etc. No range specification should be included. For example, do not enter range a keyword when using integer or down to when using STD logic vector. On the other hand, there is only one return value whose type is specified by the data type. This is what you have to remember. The return type must be a name. It cannot include a constraint. Variables defined inside a function are initialized each time that function is called. So it will be volatile. The declaration and body must conform. That is, parameters and return type must be identical. Function declaration ends with a semicolon, whereas the function body has is keyword at the corresponding point in the syntax. We'll see with an example, then you'll understand. What does it synthesize to? Each call to a function is synthesized as a separate block of combinational logic. Remember this carefully. So calling functions so many times will create so many copies of the hardware. Okay, so here for this example, we have function called as f1. Arguments are a, b, which are integer type, signal c, which is logic vector, and what it does, it returns a boolean. Okay, this is how you have to identify the functions. Then how to call a function? Function is called as a part of an expression. The expression can obviously appear by itself or be associated to a statement with a statement, either concurrent or sequential. So this is one example. X is assigned. So this is the function name. conv underscore integer is a function name. This also is a function that you must have written somewhere. Maximum of a comma b, which is assigned to y or something like that. So the function is called as a part of an expression. That is important. Now this is a very simple function which is already there as if clock tick event and clock equal to 1. A simple function. Of course, it would be redundant to write a function which which the statement is already available like this. If what does it do? It detects a positive or the rising edge of the clock. So we can write your own function to mimic the same thing, to do the same thing. For example, here in function body, I can write the name of the function as positive underscore edge, signal S as std logic, and return is boolean, whether we have detected a clock, rising edge of the clock or not. Begin, the functionality is like this, will return S tick event and S equal to 1. So this is S tick event and S equal to 1 will be true only at this particular condition. And that is returned by this positive edge function. And then you can write it something like in function call if positive underscore edge clock means what? If this is true, if this condition is true, then do something. Similarly here, it will return either true or false because the return type is boolean. Understood this? Have you understood this?
Yes, sir.
Sure?
Yes.
All right. So where can you locate the functions? Function can be inside a package plus body, package body, main code. Either it can be in entity or architecture, that is a declarative part. And when it is inside a package, it has to be inside a library. The function is usually placed in a package for, as we already said, partitioning, reuse, code sharing. It can also be located in the main code, either inside the architecture or inside the entity. When placed in a package body is necessary, which must contain the body of each function or procedure declared in the declarative part of that package. So function this is the example for function which is located in the main code. So you can see here, I've declared the function, implemented the function as a matter of fact, over here in the architecture itself, in the declarations part. All right, before begin. And then I'm calling it here. So this is one very simple way of writing the function and calling it in the main code itself. Whereas if the function is located in the package, how do I write it? Library, declare that package. In that package, I'm having so many different functions. So you can list down all the functions. Function positive underscore edge. Since we have only one function here, it will have only this. Okay. And then in package body, I'm going to actually write the logic for that mechanism, if you will. Okay. So this is inside the package. Okay. So this is important. Once you write this in a package, that package has to be referenced in your main code. So how to call that package in the main code? Like this. And then you can directly call it in the architecture. See here, if positive underscore edge clock, then do something. Work design space should be visible to the top level entity. That is what is important. All right. This is one simple function which converts std logic vector into an integer value. All right. So go through it and just try to figure out what the logic is. Just to go through this. Okay. Did you go through that, guys?
Yes, sir.
So can you describe the logic that is used? Figure out the logic. Can you figure out the logic? Basically, what is it supposed to do? So whatever is the STD logic vector value, it is supposed to convert into an integer. Means what is it supposed to do? If you have a combination, all ones, for example, okay, in that case, it is supposed to, if it is let us say 4 bits wide, that logic vector is 4 bits wide, and all of the bits are 1. Then what should be the function do? What should it return?
16.
16,
Yes.
really, or 15?
Sorry. Yes, 15.
Correct. It should be 15.
15,
So
yeah.
function is supposed to find out the integer value. So that is
Integer
what is
equivalent.
right? Okay. It is 2 to the power. So this is exponentiation 2 to the power vector tick length minus 1. In this case, the result will be in the range from 0 to. If it is a 4-bit vector, in that case, vector dash length is 4 minus 1 is 3. So it will be 2 to the power 3. That is 8 minus 1, of course. So it will be what? Length is 4. ठीक है ना? Are you able to understand this, guys?
Yes, sir.
Okay. So if vector tick high is, so you should be in a position to understand the attributes. ठीक है ना? I think we have done the attributes, no? Long back, I guess. Okay, so if it is 1, then result is 1, else result is 0. Again, going through inside this loop, I'm just multiplying the result by 2 every time whenever I have 1. Okay, so that is how you actually convert it into an integer. This is the algorithm in more detail. So vector tick length is 4, vector tick high is 3, vector tick high is 0. So this is just what it means. The very first thing, we start with the MSB. The result is 0 since that particular bit is 0. Okay, then I shift it like this. First iteration, 3 down to 0, I equal to 2 to start with. So result is 0 multiplied by 2, and result is 0 plus 1. So since that vector 2 is 1, I'm adding over here. Iteration number 2. Now I is equal to 1. So it starts with I equal to 0, I equal to 3, and then comes down like that. Okay. Result is 1 into 2, and add 2 plus 0, that is because we have 0 over here. So it continues like this. This is the last iteration. So result that is obtained is 5. See the algorithm carefully. We are going for this other than MSB, whatever bits are there after MSB, we are going for a loop there. Whereas MSB is directly evaluated. See this carefully. Okay. So have you understood the logic now? Algorithm?
Yes, I got it.
Okay. So this is how you can use it.
Yes,
Entity,
sir.
you can use it inside. Once you declare it as a package, inside the package, you can use this function very easily like this. Then let us have a look at the procedure. So what is a procedure? The procedure is very similar to function and has got the same basic purposes. The only difference is that the procedure can return more than one value. So like a function, two parts are necessary to construct and use a procedure. That is the procedure itself and the procedure call. So you can see here procedure name is the declarations. Then okay, begin, sequential statements, end procedure. The parameter list can be a constant, signal, variable. A procedure can have any number of in, out, or in, out parameters, which can be signals, variables, or constants. For input signals, mode in, the default is constant, whereas for output signals, mode out or in, out, the default is a variable. Weight, signal declarations, and components are not synthesizable when used in a function. Same is true for the procedure, with the exception that signal can be declared, but then the procedure must be declared in a process itself. Moreover, besides weight, any other edge detection is also not synthesizable with procedure, which is actually a contrasting thing to a function. A synthesizable procedure should not infer registers. We'll see an example of the procedure. So procedure, my procedure A in bit, signal B and C in bit. Signal Y is out vector, Y is X and Y both are out vector. Y is in out, whereas X is out vector. So what can we say from this? The procedure has got three inputs, A, B, C. A is constant, B and C are signals. Notice that the word constant can be omitted for input parameters, for it is a default. Since it is a default, you can omit it. Recall aware for the outputs, the default is variable. So please be careful there. There are also two return signals as compared to function, which can return only one value. Here we have two return signals, X and Y. All right. Then the procedure, how to call the procedure? Contrary to a function which is called as a part of expression, a procedure call itself is a statement. This is the basic difference. It can appear by itself or associated to a statement, either concurrent or sequential. So these are the examples of procedure calling. So you can just see that this is not directly a part of expression. You can call the procedure as a separate function itself, separate subprogram itself. Let us not confuse with function. All right, it is a statement by itself. Or you can have something like this as a part of an expression over here, which is associated with another statement. All right, so that is as far as the procedure functions and procedures are concerned. Okay, any doubts, any questions up to this point, guys?
No, sir.
I think we'll call it a day. Too many things in a day, single day will confuse you. So what I want all of you to do is whatever examples that we have seen and you must have copied them down, try on your own. Have you installed any VSDL tool, EDA tool at your end?
Xilinx.
Xilinx, which version?
I'm not sure actually. I don't have a laptop right now.
Okay. Any other person who has done it?
Sir, keel.
Karishma.
Yes, sir.
Hi, sir. Have you installed it?
Yes, sir. Keel I have in my laptop.
What do you have?
Keel software, Keel.
Keel software is not used for VHDL. Keel software is used for embedded systems development. I think you are confused. Please make sure you download VHDL tool. What I use, as I said, is Active HDL. You can use Xilinx because that is what you will be using for your practicals also.
Sir, while using Active HDL, do we need to install all packages? Like there are many packages.
Yes, yes, of course. I mean, if you
When
don't have
it takes like
any
let
storage problems like hard disk limitations, then you can install everything.
but yeah, but it takes time to download like 1.2 GB, 1.5 GB. I tried to download, but it really didn't work. It was a very huge thing.
Yeah, that is going to be there. But what you can do is you can install only for target devices corresponding to Xilinx. No need of other target devices. Okay.
Okay,
What
sure.
I have seen is I think I've got Active HDL 10 point. Let me check 5. I guess 10.1. I'll take Active HDL 10.1. That is more than sufficient for you to practice as far as the simulation is concerned. The thing gets bulky when you try to download. I mean, without try to download the target device synthesizers for target devices. Support for the boards. I mean, for the target devices. Like there are a large number of target devices, right, and the companies which manufacture them. So not necessary to have all. In fact, if you really want to only practice on simulation, up to simulation, uh, which is essential at this point of time, then I suggest that you download only Active HDL without any support for target device, and then simply carry out your simulation. Up to simulation you can do, and later on, and when it is possible for you to join back into the college, then you can copy the code directly into Xilinx, which is available in our lab, and then you can flash the devices with your code. That would be a very systematic way of doing it, because Xilinx is also very bulky, and on your laptop, even if you try to install Xilinx, which is about like 15-20 GB, the latest version, um, there is no uh, target device available with you, right? So it's no use. Whatever is available is at college in the lab, and of course over there you will not be using your laptops. So just practice for the practice of VHDL itself up to functional simulation level. You can use Active HDL. That is what I propose. Okay.
Okay, sir. Sure.
I if you are interested, I can share the link of Active HDL, but that is
Yes, sir. Yes, we want it, sir, for installing it.
all right. But again, it is okay. I'll see to it how to do it. Okay.
Okay, sir.
I'll have to upload it somewhere and then give the link to you. I'll upload it in my Dropbox and then you can have it. Okay.
So it can be easily installed, right? Active HDL.
Yes, yes, yes. Absolutely. Absolutely. Okay.
Okay,
So
sir.
yeah, so we'll stop here for today. Okay. Thank you.
Thank you, sir.